question 4.23, and it asks us which amongst all these three forces, which one is conservative. Now, to test if a force is conservative, there are numerous ways to do it. I've decided to use the curl, the definition of the curl, and to figure out if the force is equal to zero. So I'm going to find the curl of each force, and then I'll figure out if it's equal to zero. Now, to find the curl of a force, I have to take the vector product of the differentiation signs of each coordinate in respect to, and also I have to figure out in respect to the force itself. So what I did, I found the equation online using the mathematical formula handbook, and I just followed what the procedure, and I just plugged this in. So from this equation, you can break it down into this equation, and basically what you do is, it's if you trying to figure out for this term, you cover I and cross multiply these two terms over here, and that's how you figure out for I, j, k. So for k, you cover k, and then you cross multiply these two terms, you minus their products, and basically that's what we did over here. Once you figure that out, you have these three terms, and you derive in terms of the numerator, and over here it's y is z, x, and y. Once you do that, if you will figure out that dy and d of that term in terms of y is equal to 0, and that is prominent within the whole equation. So for equation A, force A, we know that the curl of it is 0, so therefore that force is conservative. And we do the same thing to the force of B, and we figure out this also that the curl is equal to 0, and this is my work, and you can look it over. I didn't rewrite this, I just use it as I just wrote it the first time just to show you how I figured out this long equation. So part B, B, the force is conservative. I forgot to write that down over here, but part B, the force is conservative. For part C, the force in C, the force is not conservative because the curl is equal to 2k. That's why. So moving on. So the second part of the equation of the question asks us to find the corresponding potential energy and verify by direct differentiation that the force is a partial derivative of the potential energy. So since I know that two equations, A and B, are equal, are conservative forces, I'm going to just stick to those. So looking at part A, so I have to figure out what is the potential. Now the equation for potential is this, and it can be rewritten to this equation over here. And what that means is that I just take all the terms in the x. So if you go back up to the equation A, so x will be, over here will be kx, and then y will be kzy, and then z will be, that's 2, sorry, k2y, and k and z will be k3z. So moving down. So moving down to the equation. So I just rewrote that and plugged in the terms accordingly, and I integrated. And once you integrate, I could see that I could take out the k's, move them outside, k over 2, move it outside, and this is my potential energy. Now they're asking me to verify that this is a potential energy by stating that if I were to partially integrate this or partially derive this, I would get the same answer as you. So basically, I should prove that this is true. So this equation can be written as this equation over here, and from then on I just plugged in what is u in terms of dx. So I didn't plug in the whole thing because I just derived from over here. So looking at this first term over here, which is the answer is right there. Looking at this first term, so they're asking you to derive u in terms of x. So in terms of x, y will go away, 3z squared will go away, 2y squared will go away, and 3z squared will go away, and all you're left with is negative k2 x squared. Now, you notice that there's a negative in front, so those two negatives will cancel each other out. That's why over here we had kx. And I did the same process for y. So the x squared will go away, and the z and 3z squared will go away, and all you're left with is 2y squared k over 2 with the negative, but that negative and this negative over here will go away. And same thing with the z. And at the end, this is the equation that I found, and you can rewrite this equation because now we have the vectors over here. You can rewrite this equation as this, and this is the same as the equation that we started off with right over here. So this checks out. So I did the same thing for part B, trying to figure out for part B potential energy. Now for part B, it's a bit tricky. I find it very tricky for part B, especially when it came into integrating defining the u. Now you may notice that I keep on I leave out the change in u, and the reason why I leave out the change in u is because I assume that u starts from the origin. So if I start from the origin, I don't have to consider the change in u because it's starting from the origin. So that's why the change goes away. So integrating over here, I just plugged in what are the terms for these equations in respect to equation B, and the tricky part comes when you have to integrate. Now when you integrate these two terms, you have to get the same things, which is kxy. So my theory is if you get kxy, normally you have to add these two as a potential, but for some odd reason, I don't know if that's correct because the answer is supposed to be negative kxy, and I don't really know why it's that, but my explanation is that since this is a potential energy in the x direction and also in the y direction, so I guess this will be the potential energy in that of the whole system. But moving on, I had to verify that this term over here is equal to the force if I were to take the partial differentiation of it, and if you plug that into the u over here and you derive it in terms of x, y, and z, you do find that this is the equation you're left with, and at the end we are left with this equation. So that was standard 4.1. The only issue we had over here was just figuring out how this equation turns out to be negative kxy. So I'm missing an equal sign over here. So this is not a whole term. So I'm missing equal sign over here. All right. Thank you.